Hello everyone, and thanks for watching Edupedia World videos. In this session we'll look at mathematical expression for writing Kp. In the previous one we looked at mathematical expression of Kc and how can we write it for different reactions. So we'll do the same thing here, alright, but just for Kp. So for that you must first remember or recall that Kp is written in terms of partial pressures. Okay, so this time at equilibrium we do not use molarities of reactants and products, but instead we use partial pressures of reactants and products present at equilibrium to write the expression of Kp. This we have already seen in a previous session, right? So now we'll just take actual examples, okay, of reactions and see how can we actually write the expression of partial pressure and then subsequently write the expression of Kp. So let's start. For the first example we will use a simple method. Okay, this method is not applicable everywhere, okay, but it is the simplest way of writing Kp. Let's say you have a reaction in which all the reactants and products are gaseous. Okay, so N2 and H2 reversibly forms ammonia. This is the reaction and the balancing of the reaction is given in this form. Alright, now the question they have asked is to calculate or find the expression of Kp. So how can we do that? Right? So this method which I am about to show you is applicable only when temperature is constant. Okay, so this condition is usually always true. In your syllabus every reaction will have pretty much constant temperature while writing any of the expressions. Okay, and the second condition, volume of your container, the container inside which all the reactants and products are present, that is the container in which the reaction is actually taking place. So if the volume of that container is also constant, then we can use this method. Okay, so only when this condition is satisfied is this method applicable. Okay, so let's see now. So this method basically says that if temperature and volume are constant, then I can directly say that my number of moles are going to be proportional to pressure. Okay, or a better way of saying it is my pressure is proportional to number of moles. Okay, that is to say partial pressure of any given gas is also going to be proportional to moles of that particular gas. So here I have three different gases. Okay, so instead of writing moles, for example while writing Kc we saw that I would have written here at T is equal to 0 I have A moles of nitrogen, B moles of hydrogen, and let's assume 0 moles of ammonia. Then at T is equal to T equilibrium, okay, at T is equal to T equilibrium I can write A minus X, B minus 3x moles of hydrogen and 2x of ammonia. That is X moles of nitrogen has been consumed, so 3x moles of hydrogen will be consumed and 2x of ammonia will be formed. So A minus X and B minus 3x are moles of nitrogen and hydrogen respectively still left unreacted in my container. Okay, so we did this for moles. Alright, and we can also always do this. This thing is always applicable. Okay, because stoichiometric coefficients always represents molar proportions. But the thing is, now since temperature and volume is constant, okay, I know that for ideal gases, okay, assuming ideal gas, PV is equal to nRT, which means pressure is directly proportional to number of moles. That is to say that partial pressures of each of the gas is going to be proportional to the moles of those gas. So I can write similar expression in terms of pressure. Instead of writing it in terms of moles, okay, I can write a similar expression in terms of pressure. Right? So I can assume that at T is equal to 0 I had P1, okay, as the partial pressure of nitrogen and P2 as the partial pressure of hydrogen, and let's say there was no ammonia present. Then by the time equilibrium is achieved, okay, so amount of nitrogen left with me is P1 minus P. That means P, okay, P is the amount or the proportion of nitrogen consumed, which means the proportion of hydrogen or the amount of hydrogen consumed, okay, will be 3P, and that of ammonia formed will be 2P. So here P1 and P2 were partial pressures of nitrogen and hydrogen respectively, which means P1 minus P and P2 minus 3P are partial pressures of nitrogen and hydrogen left at equilibrium, and 2P becomes the partial pressure of ammonia formed by the time equilibrium is achieved. Okay, so here now I know that the expression of Kp is simply equal to partial pressure of ammonia whole square divided by partial pressure of nitrogen, okay, into partial pressure of hydrogen cube. Alright, so this is the expression for Kp. So now I simply substitute the values. Partial pressure of ammonia I know is 2P, okay, partial pressure of nitrogen is P1 minus P, and partial pressure of hydrogen is P2 minus 3P whole cube. Okay, so if you know the value of P, alright, if they have given you P1, P2 and P, which they will give you in the question, you can simply find the value of Kp using this expression. Okay, so this is a very simple method where what we used to do for moles, okay, we did for pressure. Alright, so we assume that the stoichiometric coefficient also represents, instead of molar ratio, they also represent pressure ratios, okay, ratio of partial pressures of each of the reactants and products. Alright, and hence we were directly able to calculate the partial pressures at equilibrium and hence write the expression for Kp. But once again, this is applicable only and only when temperature and volume are constant. So let's look at another method, a more complicated method, but also a more accurate one. Accurate in the sense that it will be applicable everywhere for all the reactions. Okay, so there is no exception to that method. Alright, but obviously since we are writing Kp, okay, you must have gaseous components. Alright, Kp is written in terms of partial pressures, so you must have components there which are exerting pressure in a significant amount, so that we can measure that amount, that pressure. Let's say this time your reaction is slightly different. Say we are talking about decomposition of PCl5. Okay, so PCl5 decomposes reversibly into PCl3 and Cl2. Alright, so now my goal is again to write the expression of Kp, okay, and I know that Kp is simply going to be equal to partial pressure of PCl3 at equilibrium into partial pressure of chlorine at equilibrium divided by partial pressure of PCl5 at equilibrium. Okay, so I just need to find partial pressures at equilibrium. So how can I do that? Okay, if I'm not assuming volume or temp, okay, to be constant, or temperature, though temperature will always be constant, okay, in all our questions, but let's say we are not making any assumptions, so how can I write this expression? Alright, temperature has to be constant if you are defining a particular value of Kp. Alright, so what we do know is that partial pressure, okay, from the Dalton's law that we studied in gaseous state, we know that partial pressure of any given gas is equal to mole fraction of that gas into total pressure. Okay, so we will use this equation over here to substitute the values of partial pressures at equilibrium. Once again, partial pressure of any given gas in a mixture is equal to mole fraction of that gas in the mixture multiplied with total pressure of the mixture. Okay. So let's say that at T is equal to 0, okay, moles of PCl5 is A and that of products are 0 and 0. So by the time equilibrium is achieved, okay, I can say that moles of PCl5 left are A minus X. That means PCl3 and Cl2 formed are X and X. So now I'm writing, okay, I'm taking stoichiometric coefficient, I'm writing stoichiometric coefficient ratio as molar ratio. Okay, these are moles I have taken over here, and this is always applicable. Okay, so this time I'm not writing pressures, partial pressures in terms of stoichiometric coefficient. Okay, so now I know that these are my individual moles at equilibrium, and I want to convert these moles to partial pressures. So how will I do that? First thing, okay, find out the total pressure. Okay, so total pressure PT, okay, is usually given to you in the question, because you cannot otherwise calculate it. Okay, or you will have to use the method PV is equal to nRT, where n is total moles, to find total pressure. Okay, you cannot, there is no way to otherwise calculate it, okay, apart from that, at least not from what you know. So total pressure, just know, is also sometimes referred as equilibrium pressure, okay, of your container, because it is the pressure exerted at equilibrium by all the reactants and products together. Okay, this same pressure is also called total pressure, okay, of the container at equilibrium. All right, so this value will be given to us. Next, total moles. Okay, in order to find mole fraction, we need the value of total moles at equilibrium. So what are total moles? They are simply moles of PCl5 plus moles of PCl3 plus moles of Cl2, okay, which will be moles of PCl5 are A minus X, then plus moles of PCl3 are X, and Cl2 X. So this is A plus X. Alright, so now I can directly write the expression for mole fraction. Right. So mole fraction is simply moles, okay, moles of individual substance divided by total moles. So mole fraction of PCl5 at equilibrium will be, okay, A minus X divided by total moles, A plus X. Mole fraction of PCl3 at equilibrium will be moles of PCl3X divided by total moles, A plus X. Similarly, mole fraction of chlorine will be X divided by A plus X. So these are mole fractions of each of the reactant and product at equilibrium. Now if I multiply these mole fractions, okay, with PT, I will get my partial pressure. Okay, so these are partial pressures at T equilibrium. Okay, so in order to get the expression of Kp, I will simply substitute these values, okay, in this particular expression over here. Alright, so once I substitute these values, I will get my final answer, that Kp is simply equal to xpt divided by A plus X whole square, okay, because partial pressure of PCl3 and Cl2 is both xpt by A plus X, and divided by partial pressure of PCl5, which is A minus X divided by A plus X into PT. Alright, so this is the correct expression for Kp, and this method, okay, of writing Kp in terms of partial pressure and calculating those partial pressures using mole fractions of reactants and products is always applicable. Though it is longer, okay, it is more tedious, but it is very nice and accurate method. The previous one, where we simply assume that stoichiometric coefficients can also be written as ratios of partial pressures, okay, so that method is not applicable everywhere. Okay, so it will vary from question to question, but this method you can use in all the questions. Okay, so in the next session we'll look at some numerical examples, 1 or 2 questions in which we'll have to actually calculate Kp. Okay, and we'll try and use both the methods in some or other question while doing that. So until then, and once again, thanks for watching Edupedia World videos.